The universe is not silent. You've been told that your whole life, that space is a vacuum, that a scream in orbit fades into nothing, that if you pulled off your helmet out there, the last thing you'd experience is silence. And that part is true, but it's also the smallest, least interesting part of the story. Because while sound in the traditional sense, air molecules bumping into your eardrum, genuinely cannot survive the vacuum of space, the universe is still shaking, humming, pulsing and screaming in almost every other way physics allows. We've just spent the last 60 years building machines specifically so we could finally hear it. By the end of this video, you'll understand how a black hole, 250 million light-years away, has a note, how our own sun rings like a bell you could never touch, how a dead star can tick like a lighthouse clock, accurate enough to rival an atomic clock, and how the fabric of space-time itself let out a chirp in 2015 that changed physics forever. The universe isn't quiet. We just weren't listening to the right thing. Let's set the scale of what we're actually talking about, because it's easy to hear the sound of a black hole and picture something out of a horror movie, playing through empty space the way a scream travels through a hallway. That's not what's happening in any of these cases, and being honest about that is actually the most interesting part of the story. Some of what you're about to hear is real, physical sound, pressure waves traveling through an actual medium, the same basic physics as a voice traveling through air, just at a scale and pitch no human ear could ever process. Some of it is something else entirely, electromagnetic radiation, or gravitational ripples in space-time itself, translated, sonified, into the range of human hearing, because that happens to be a spectacular way for us to interpret data we could otherwise only see as squiggly lines on a graph. Both are real, both are useful, but they are not the same thing, and by the end of this video you'll be able to tell the difference every time you hear one of these recordings again. Let's start with the one that's easiest to misunderstand, because it involves a spacecraft that is, right now, farther from home than anything humans have ever built. NASA's Voyager 1 launched in 1977, and on August 25, 2012, it did something no human-made object had ever done before. It crossed the boundary of the heliosphere, the vast magnetic bubble the sun inflates around our entire solar system, and became the first spacecraft to enter true interstellar space. Voyager didn't know it had crossed the moment it happened. There's no line painted in the void. Scientists figured it out months later, after data trickled back to Earth from an instrument called the Plasma Wave Instrument, led by physicist Don Gurnett at the University of Iowa. Twice. Once from October to November of 2012, and again from April to May of 2013. That instrument picked up something extraordinary. The electrons in the thin, ionized gas surrounding the spacecraft were oscillating, vibrating back and forth at frequencies that happened to fall between a few hundred and a few thousand hertz. That's the same range as human hearing. So Gurnett's team did something almost embarrassingly simple. They amplified the signal and played it through a speaker, and it worked. Interstellar space made a sound, a rising, keening tone, triggered by shockwaves from solar storms slamming into that thin interstellar gas months or years after leaving the sun, the way a coronal mass ejection might take a year or more just to reach a spacecraft that far out. Strictly speaking, Gurnett was careful to point out, the instrument doesn't detect sound in the way your ear does. It senses waves of electrons in plasma. But because that plasma is a real physical medium, and because those oscillations genuinely occur at audible frequencies, this is about as close as humanity has ever come to literally hearing another region of space. Voyager 1 is still out there right now, in a region scientists once assumed was nearly empty, still listening. So if a starship-sized bubble of interstellar gas can ring, what about something with real mass under it, something like a star? Let's pause here, because this next part surprised even the scientists who found it. In the early 1960s, physicists Robert Layton and Robert Noyes were studying the sun's surface and noticed something they weren't looking for. Parts of the surface were rising and falling, rhythmically, on a cycle of about 5 minutes. At first, it looked like noise. It wasn't. What they'd stumbled onto is now called helioseismology, the study of the sun's interior by listening to how its surface vibrates, the same basic principle earthquake scientists use to map the inside of our planet. The sun isn't struck by one single event the way Earth is struck by an earthquake. Instead, the entire roiling, churning convective zone, just beneath its visible surface, is constantly generating turbulence, and that turbulence excites sound waves, real acoustic pressure waves, moving through the sun's plasma the exact same way sound moves through air, just through a medium hot and dense enough to carry them for hundreds of thousands of miles. Trapped inside the sun, bouncing and interfering with each other, those waves settle into resonant patterns, and the surface of the sun ends up oscillating in millions of overlapping frequencies at once. Scientists have described it as a bell struck continuously by countless grains of sand, or a pipe organ with a million pipes all sounding together, or an orchestra endlessly tuning. For decades, instruments like the Michelson Doppler imager aboard the SOHO spacecraft and later the helioseismic and magnetic imager aboard the Solar Dynamics Observatory have measured this by tracking tiny Doppler shifts in the light coming off the sun's surface, shifts caused by gas moving toward us or away from us as it oscillates. Physicist Alexander Kosovichev, working with this data at Stanford, sped up recordings of the sun's low-frequency oscillations by a factor of roughly 42,000 to bring them into audible range, and the result is an actual recording of our own star's interior resonance, a deep, slow, pulsing hum that never stops, because the sun's convective churn never stops. This isn't decoration. Helioseismology is how physicists have mapped the sun's internal rotation, probed the temperature of its core, and tracked the machinery that drives space weather, all from listening to a star that is 93 million miles away and that we can never physically touch. Now, if a star can ring like a bell, what happens when a star dies? Specifically, when it collapses into one of the densest, strangest objects in the universe. On the night of November 28, 1967, a 24-year-old graduate student named Jocelyn Bell was combing through more than 100 feet of chart recorder paper a day, data from a radio telescope she had personally helped build in a field outside Cambridge. She was looking for quasars. What she found instead was a signal so regular, so mechanically precise, that at first her own supervisor assumed it had to be man-made interference. It repeated every 1.337 seconds, with a pulse width of just a few hundredths of a second, over and over, never drifting. It was so perfectly rhythmic that the team half-jokingly nicknamed it LGM-1, Little Green Men 1, because a signal that precise sounded, briefly, like it could be artificial. Bell ruled that out herself within weeks, when she found a second, unrelated source doing exactly the same thing from a completely different part of the sky. What she'd actually discovered was the first known pulsar, now catalogued as PSR B1919+21, and it rewrote astrophysics. Pulsars are neutron stars, the collapsed cores left behind when a massive star goes supernova, packing more mass than the sun into a sphere roughly the size of a city. They spin, some many times per second, and as they spin, powerful beams of radio radiation sweep out from their magnetic poles like a lighthouse. If Earth happens to sit in the path of that beam, we get a pulse, once per rotation, with a precision that rivals an atomic clock. Convert those radio pulses to audio, and you get an unmistakable rhythmic tick, the closest thing the universe has to a heartbeat, generated by the crushed, spinning corpse of a star. That single discovery would go on to give physicists a tool for testing general relativity, detecting gravitational waves indirectly decades before LIGO existed, and navigating deep space. It's also worth pausing on something else about that story. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars, but it went to Bell's supervisor, Anthony Hewish, not to Bell herself, a decision that remains one of the most debated snubs in the prize's history. It's worth sitting with how strange that discovery really was in the moment. Bell wasn't running some automated search algorithm. She was reading paper by hand, day after day, and the signal she found occupied roughly a quarter of an inch on a chart that stretched for miles. She only caught it a second time because something in the back of her mind insisted she'd seen that exact pattern before, from that exact patch of sky. When she and Hewish switched to a faster recorder to check, the source went quiet for an entire month before it finally reappeared, on the night of November 28th, and gave up its secret. Within a year, astronomers had found dozens more of these clock-precise radio sources scattered across the sky, and by 1968 physicist Thomas Gold had worked out what they actually were. Not beacons, not aliens, but the spinning, magnetized remains of dead stars, sweeping the galaxy with radio light the way a lighthouse sweeps a coastline. Today, arrays of pulsars are used as a galaxy-spanning gravitational wave detector in their own right, astronomers timing their pulses across years to catch ripples in space-time far too slow and low frequency for LIGO to ever register. Pulsars are radio waves, not literal sound, translated into rhythm we can hear. Saturn does something similar, and it is, without exaggeration, one of the eeriest recordings ever pulled from another world. When NASA's Cassini spacecraft arrived at Saturn in 2004, it carried an instrument called the Radio and Plasma Wave Science Instrument, built at the University of Iowa under the same Don Gurnett, who would later listen in on Voyager's interstellar crossing. Cassini picked up something called Saturn kilometric radiation, intense radio emissions generated in the planet's polar regions, tied directly to Saturn's auroras, produced as electrons spiral along the planet's magnetic field lines the same way charged particles do above Earth's own poles. Converted into the audible range, scientists Bill Kurth and Gurnett described the result themselves. It sounds like a spinning air raid siren, rising and falling in bursts that track Saturn's own rotation, roughly every 10 hours and 39 minutes. Though strangely, the northern and southern hemispheres don't keep quite the same rhythm, and the two have actually been observed to swap rates over the years in ways that still aren't fully explained. None of this is sound in the physical sense. There's no medium out there for it to travel through. It's raw electromagnetic radiation, radio waves shifted down into a pitch human ears can process. But the pattern in that siren isn't decoration either. It's telling scientists something real about the structure of Saturn's magnetosphere, about how radio sources drift up and down along magnetic field lines, and about a planet whose interior rotation rate is so wrapped up in its magnetic field that scientists still don't have a clean single number for how fast Saturn actually spins. Cassini spent 13 years in orbit gathering this kind of data, before its mission ended deliberately, in 2017, when controllers steered it into Saturn's atmosphere to burn up rather than risk it drifting into and contaminating one of the planet's potentially habitable moons. Every recording of that air raid siren shriek that exists today was captured during those 13 years, from a spacecraft that no longer exists, listening to a planet that is still, right now, singing exactly the same way. So far, every one of these examples has been either an actual sound wave moving through a physical medium or an electromagnetic signal we've chosen to translate into pitch. Now, here's where it gets stranger, because the next example does something almost nobody expects. It's real acoustic sound, coming from one of the most violent objects in the universe, at a scale so vast it becomes almost impossible to picture. At the center of the Perseus galaxy cluster, a structure of hundreds of galaxies bound together by gravity, roughly 240 million light-years from Earth, and 11 million light-years across, sits a supermassive black hole. Galaxy clusters aren't empty between their galaxies. They're filled with enormous amounts of superheated gas, reaching temperatures over 180 million degrees Fahrenheit, and that gas is a medium sound can actually travel through, the same basic requirement as air carrying your voice. In 2003, astronomers using NASA's Chandra X-ray Observatory discovered something remarkable. The black hole at Perseus's center was sending out pressure waves, genuine sound waves, rippling outward through that hot gas, the same physical phenomenon as a drum skin pushing air, just on a scale that swallows galaxies. Those waves translate to a single note, a B-flat, roughly 57 octaves below middle C. To put that in perspective, that note's frequency corresponds to a wave that completes one single oscillation roughly every 10 million years, a pitch so far below anything a human could ever perceive that scientists had to shift it upward by 57 to 58 octaves, resynthesizing it into our hearing range by scaling its frequency up by a factor of somewhere between 144 quadrillion and 288 quadrillion, just to make it audible at all. Around the same time, a second black hole, at the heart of the galaxy M87, the same black hole the Event Horizon Telescope famously imaged in 2019, with a mass roughly 6.5 billion times our Sun, got a sonification of its own, this time built from X-ray, visible light, and radio data scanned across the image and mapped into different vocal ranges. Neither of these recordings is a black hole singing, in any mystical sense, but the Perseus sound in particular is not a metaphor. It's the deepest note ever detected in the universe, and it is, technically, genuine sound, still rippling outward through hundreds of thousands of light-years of gas, right now, exactly as it has been for millions of years. Let's take stock for a second, because we've covered a lot of ground. Real sound in interstellar plasma and inside stars and galaxy clusters, and sonified radio data from pulsars and planets. There's one more category, and it might be the strangest of all, because it isn't sound, and it isn't light, and it isn't even a wave moving through anything at all. It's a ripple in space-time itself. On September 14, 2015, at 09:50:45 UTC, twin detectors of the Laser Interferometer Gravitational Wave Observatory, one in Hanford, Washington, and one in Livingston, Louisiana, registered an almost impossibly tiny stretching and squeezing of space itself, arriving within milliseconds of each other. The signal, now catalogued as GW150914, had been traveling for more than 1 billion years, generated by two black holes, one about 36 times the mass of our Sun, the other about 29, spiraling into each other and merging into a single black hole, roughly 62 times the Sun's mass. Do the math on those numbers and something doesn't add up, and that's the point. 3 entire solar masses simply vanished, converted directly into gravitational wave energy in the final fraction of a second of the collision, radiated outward at a peak power greater than the combined light output of every star and every galaxy in the observable universe combined, just for an instant. As those two black holes spiraled together, the frequency and amplitude of the wave they produced increased, climbing in what physicists call a chirp, before peaking at the moment of merger and then settling into a fading ringdown, as the newly formed black hole, initially distorted by the violence of the collision, rang itself back into a smooth sphere. The entire visible signal lasted about 0.15 seconds. When scientists shifted that gravitational wave data into the audible range, not because it is sound, but because its frequency happened to land conveniently close to what a human ear can process. The result is an unmistakable rising whoop, cosmic and mechanical at once, a genuine chirp from the fabric of the universe itself. It was the first direct detection of gravitational waves in history, a full century after Einstein predicted they should exist, and it opened up something astronomers now call multi-messenger astronomy, the ability to study the same cosmic event through light, through particles, and now through the actual geometry of space-time. What makes this detection different from every other example in this video is that there was no medium involved at all. Voyager's plasma waves needed ionized gas to oscillate through. The Perseus black hole's note needed the cluster's superheated gas to carry it. Even Saturn's radio siren and the Sun's helioseismic hum are, at bottom, still waves moving through or generated by matter. A gravitational wave doesn't need anything to travel through, because it isn't a disturbance in some substance. It's a disturbance in space and time themselves, stretching and squeezing the actual distance between objects as it passes. When GW14914 crossed the Earth, it briefly changed the length of LIGO's 4-kilometer detector arms by a fraction smaller than the width of a proton, and it did the same, imperceptibly, to everything else on the planet, including you, if you happen to be alive on September 14th, 2015. There is nothing else on this list that behaves like that. It's the closest thing physics has to proof that the universe itself can ring. I want to be careful here, because it would be easy to walk away from all this thinking we've simply cracked space open, and it's been shouting at us the whole time. That's not quite right. Every single one of these signals required decades of purpose-built instruments, sitting in exactly the right place, tuned to exactly the right frequency, run by teams willing to spend years extracting a whisper from an ocean of noise. Voyager's plasma waves were only heard because a scientist happened to notice a rising tone buried in months-old telemetry. LIGO's detectors have to isolate a signal smaller than 1,000th of the width of a proton, which is why there are two facilities 2,000 miles apart. A real gravitational wave has to show up in both, almost simultaneously, or it doesn't count. None of this was inevitable. It was built. And that's really the answer to why anyone keeps doing this, why you'd spend a career designing an instrument sensitive enough to hear a black hole a billion years away, or flying a spacecraft for decades just to catch 2 months of plasma oscillations. Each of these signals is a measurement tool disguised as a curiosity. The sun's helioseismic hum let physicists map a stellar interior we will never physically visit. Pulsar timing gave astronomers a natural network of cosmic clocks, precise enough to test Einstein's general relativity and hunt for gravitational waves from the ground up, years before LIGO existed. The chirp of GW1414 didn't just confirm gravitational waves were real, it gave physicists a direct read on the mass, spin, and violent history of two black holes that no telescope could have ever seen, because merging black holes emit no light at all. This isn't astronomy as spectacle. It's astronomy using every channel physics allows. Because sound and light and radio and gravity each carry information the others simply cannot. A telescope can only ever show you the outside of things. The light an object happens to emit or reflect. Sound and its cousins let scientists reach inside. Helioseismology is the only reason anyone knows what the sun's interior rotation looks like, because no telescope, however powerful, can see through 400,000 miles of opaque plasma. Gravitational waves are the only reason anyone has ever directly measured the properties of two colliding black holes, because a black hole merger releases essentially no light at all. By definition, nothing escapes a black hole, including the moment two of them become one. If we'd only ever built instruments that gather light, entire categories of the universe would have stayed permanently invisible to us. It took listening, not just looking, to close that gap. And we are, right now, building the next generation of ears. The ground-based detectors that caught GW1500914, LIGO and its European counterpart Virgo, can only hear gravitational waves at relatively high frequencies because Earth itself is far too noisy, too full of seismic rumble and passing trucks and ocean waves to pick up anything lower. So the next step is to leave Earth entirely. The Laser Interferometer Space Antenna, LISA, led by the European Space Agency in partnership with NASA, is now in active development after formal adoption in January 2024, with a launch currently planned for the mid-2030s. LISA won't be one spacecraft. It will be 3, trailing behind Earth in its orbit around the Sun, arranged in a perfect triangle 2.5 million kilometers on a side, holding that formation using lasers precise enough to measure changes smaller than the width of an atom across that entire distance. Once it's operating, LISA will be able to hear gravitational waves at frequencies no ground-based detector ever could. The slow, deep rumble of supermassive black holes merging at the centers of colliding galaxies, events that could take not fractions of a second, but years to fully play out. Which brings us back to where we started. Space is a vacuum. Sound, in the strict sense your body understands it, genuinely cannot cross it. That much of the myth is true, but somewhere along the way, that one narrow fact hardened into a much bigger, much less true idea, that space is empty, that space is quiet, that there is nothing out there to notice us or be noticed. The universe we've actually found, Every time we've built an instrument sensitive enough to check is the opposite of that. It is plasma vibrating in the dark beyond our solar system. It is a star ringing continuously, quietly, for billions of years, whether or not anyone is listening. It is a dead star ticking with the precision of a clock, and a gas giant howling with its own auroras, and a black hole 250 million light-years away holding a single, impossibly low note for longer than our species has existed. It is space-time itself, chirping for the briefest instant, as two black holes finally became one. None of it was ever silent. We just hadn't built the ears yet. Thanks for watching, and I'll see you in the next one.